Okay, welcome back. This will be the first of our screencast videos on vectors, continuing on with the material in Chapter 3. So we're on, I guess this is, if you're following along in the textbook, we're at section 3.2 here in the textbook. Um, so in the previous video, we introduced the Cartesian coordinate system using coordinates to identify points in 2 and 3 and then higher dimensional space. And today we're going to talk about vectors. And so we think of vectors as kind of giving us a method for navigating between points, as giving us sort of directions as how to get from one point to another. Now there are really throughout mathematics, this word vector pops up all over the place, and it has a lot of different meanings depending on the context. And there are a lot of areas that use vectors and have a lot of applications. So anyone who's done high school physics has encountered vectors, and you're used to thinking of vectors as some sort of directed quantity, something that has both a direction and a magnitude. Magnitude you think of somehow as being like length, but often you think in terms of velocity, force, acceleration, maybe like the electric field, magnetic field, things like this. The strength of the field corresponding to the magnitude and then the direction in which it's pointing. In mathematics, vectors are sort of viewed as algebraic objects. We're going to see that as we move through this course, that vectors are things that you can add together. You can multiply them by numbers, and there are certain rules that these operations have to follow. And so mathematically, that's where we kind of look at vectors, is so algebraic objects, things that follow certain rules of algebra. You might think of vectors in terms of data analytics. You've got some information, you want to put it in some sort of order so you can keep track of it, but you might need to also manipulate that data. You might need to, take averages, do things like this. Or maybe you're dealing with graphics processing, things like this. There are all sorts of places where vectors show up. And one of the things that we'll see is that these kind of algebraic and geometric points of view which dominate a lot of the discussion of vectors. They're really just two ways of looking at the same thing, and both have their advantages, right? The downside to the algebraic point of view is you don't have a picture that you can work with. The downside to the geometric point of view is that it's not precise. You're drawing pictures, and there's always a little bit of room for error when you draw a picture, right? You can't draw a line that is infinitely thin. You can't draw a point which is really a point. There's always some size to a point, and so you can't do things accurately by simply drawing a picture. Okay, so like I said, a geometric vector. This is something that's viewed as an arrow. So if you're in 2 dimensions, 3 dimensions, you might have sort of something like this. Let's draw a two-dimensional picture. So let's say I'll put it down here in the corner. You've got a pair of coordinate axes, and you've got a couple of points. You've got a point here, a point P. You've got some other point Q over here, and a vector is just going to be the arrow between them. So you draw a vector from a point P to a point Q, and the notation we would use if these 2 points are specified, you would call this, you'd put a little arrow over the letters PQ to indicate that we're talking about a vector here. So this is the idea of a geometric vector. You think of this arrow, and the way you can kind of get all the information about this arrow is contained in the coordinates for the 2 points. So this point is sometimes called the tail of the vector. The point Q is sometimes called either the head or the tip of the vector. And now this, I've drawn the two-dimensional picture, but this is a picture that you can draw in any number of dimensions. Well, okay, you can draw it in 2 or 3 dimensions. You can kind of imagine that you could do the same thing in higher dimensions, but you can't really draw the picture anymore. So the thing to realize here is that what's important about this vector, about the 2 points, is really the differences between the coordinates. So the difference between the first coordinates, the second coordinates, the third coordinates, and so on, right? I can kind of take this vector and I could break it down. I could draw, this triangle in, right? And I could break it up into sort of horizontal and vertical pieces, and the length of the horizontal piece, is going to be the difference between the x coordinates. The length of the vertical piece is going to be the difference between the y coordinates. And kind of the way you might want to think about it is if this point P, right? So if P is equal to, maybe this is the point x1, y1, and Q is equal to the point x2, y2. So then the vector PQ would be this vector x2 minus x1, y2 minus y1, and so we record these numbers, right? And now that we've described a vector using numbers, we have something which is precise, right? We're not just relying on this picture of an arrow. We have these numbers that we use to encode the vector, and numbers are precise. The arrow is not so precise, but the numbers are. And what these numbers are telling us, these numbers are really telling us how to get from the point P to the point Q. They're saying, okay, you start at this point x1, y1, and well, what does the first component, this x2 minus x1, what is it telling me? Well, one way to think about it is it says, okay, you start at a point that has a coordinate x1. Now you add on the corresponding part of the vector x2 minus x1, and you add that on, and then you see what's the number you get to. Well, notice that if you simplify here, the x's, those cancel out, and leaves you with simply x2. And of course you can do that for the y coordinate as well. And so what that vector is telling you, this vector gives you in this case a pair of numbers, and it's telling you, okay, take these numbers, add them to the coordinates of the point P, and you will end up at the point Q. So it's telling you how to get from one point to another. Okay, so just to give you a quick example, let's take this two-dimensional picture, and let's say that maybe P is equal to the point 1 minus 4, maybe Q is equal to the point minus 5, 2, and so the vector PQ would be, and again remember, you got to be careful here that one of the common mistakes is to subtract in the wrong order. You always want to do tip minus tail, right? So this vector from P to Q, we want the differences between the head and the tail. So we want to do tip minus tail. So we do the coordinates for the tip, 5, minus 5 and 2, and we subtract off the coordinates for the tail. And again, be careful about signs. You're subtracting minus 4 when you subtract the y coordinates there. And so you get minus 5 minus 1 gives you minus 6. And 2 minus minus 4 becomes 2 plus 4. So you get the vector minus 6, 6. Okay? And again, just as a reminder, you're doing this kind of head minus tail or tip minus tail rule to construct this vector. And again, as I said, notice that if you take those numbers, minus 6 and 6, if you add them to the P coordinates, you will end up with the Q coordinates. Okay, so one of the things that you want to kind of keep in mind when you're working with vectors, and one of the conventions that we take, is that, if we think of a vector as a geometric object, as something that's characterized by magnitude and direction, then we would say, well, any two vectors that have the same magnitude and same direction should be viewed as the same vector, regardless of how we draw them, in our coordinate system. So if I had, if I had two vectors, say here, and I'll try to draw them carefully, and here, that are pointing in the same direction, and they have the same length, I would say, well, those are basically the same vector, right? I've just drawn it with the tail at two different places. And so you can see that this works if you, if this is sort of, P, and this is Q, and down here is R, and this is S, then one of the ways that you kind of get the same vector, you can see that, well, however I move the tail, right, whatever direction and distance I move the tail, and in fact you can kind of think of that as a vector too, right? You kind of have this guy here, so that vector and that vector, those must be the same. These must also be the same. Maybe call that guy W, right? However I change the tail, I must change the tip by the same amount, or else I'm going to affect either the magnitude or the direction, right? If I lower the tail but I don't lower the tip, I'm going to end up rotating that vector. So the way you kind of represent this numerically is you'd say, well, if P, P was the point x1 down to xn, Q was the point y1 down to yn, as on the previous slide. So if I add, whatever numbers I add to the coordinates of P, say a1, a2 up to an, if I add the same numbers to the coordinates of Q, then I get two new points, and kind of the distance and direction from R to S is going to be the same as from P to Q. And you can see this in terms of vectors because, if you calculate this, the vector from R to S, we do again head minus tail. So you do y1 plus a1, and you subtract off x1 plus a1, and then you do that for the second coordinate and the third coordinate, and so way down, all the way down to the last one, yn plus an minus xn plus an. And then of course, if you push that minus sign through, this is going to give you minus x1 minus a1. So these guys, those are going to cancel. They're going to cancel. They cancel all the way along, and you end up with simply y1 minus x1 all the way down to yn minus xn, and that's the vector pq, right? So if you translate the vector, if you make the same change to the tail that you make to the tip, you're not actually affecting the vector. You're not affecting these numbers that give us the information about the vector. So we don't care about location. We only care about the length of the vector and the direction of the vector. Okay. All right. Now, because you can draw a vector anywhere you want, one of the most convenient places to draw that vector is you put the tail at the origin, and you get this notion of a position vector. So if you think of kind of a three-dimensional picture, the origin being here, 0, 0, 0. If I have any other point in space, I have a point, say, x, y, z, sitting there in space, then I can draw the vector from the origin to that point. And so this would be, so if this is the point P, and the origin, we often just refer to the origin as O. So this vector V here, right? So V is going to be this vector from the origin to P. And so of course I'm going to get x minus 0, y minus 0, z minus 0. We don't bother to write the minus zeros. We simply get x, y, z. Okay. So, the vector v, it contains exactly the same information as the point P. It contains these three numbers, these three coordinates, x, y, z, telling us where we are in space, right? There's a bit of a kind of a change in perspective here. Rather than thinking about a point, we're thinking about an arrow that's kind of directing us to that point. And we'll see that there's also a major practical difference. When we get to the next video, we'll see that the practical difference here is going to be that although it doesn't really seem to make any sense to add points, if you kind of imagine you have 2 points in space, what does it mean to add them together? That doesn't seem to make any sense. It does make sense to add vectors, and this is one of the big advantages of vectors, is that we can in fact add them. And that's one of the advantages of changing your perspective from simply working with points to working with vectors. And that's going to be something we discuss in the next video.